Hello everyone, this is the University of South Florida ProjectIgnis, and today we'll be presenting our CDR report. To reintroduce ourselves, here we have Iris, the team lead, Irvi as communication lead, Hasman as secretary and scribe, last but not least, Sarah, our finance and research lead.
The team's problem statement is as follows. A reusable, universal, and durable thermoregulation system designed to mitigate perceived cold discomfort at -20°C in trauma-related amputees participating in para-bobsled and skeleton events.
Here's what we've done for this project over the fall semester. So far, we've developed our needs statement, researched the disease state, existing solutions, gap analysis, market landscape, business models, regulations, and made over 100 ideas for prototypes. We narrowed down those ideas and did some interviewing and shadowing, and we made 3 prototypes. For the final week of the semester, we will present our proposed solution and the steps we took to get to this point and our future plans.
For conflict selection, we chose the best design based on the flexibility of the heating element for our athlete to ensure that they're not restricted by a device and have free mobility range, as well as the cost, where it is low yet effective. And lastly, its customizability, where we are able to control the sensor to tailor to our parameters. From our previous PDR, we showed our 3 final designs. We wanted a flexible, inexpensive, and customizable heating element for our project. To go over the different designs, for the first one, when we were researching for thin film microchips, we noticed that there were not that many available in the market for us to purchase. All these chips were still being developed, and therefore we did not have the opportunity to purchase them and experiment with them. Another thing is the problem with its flexibility. We want our device to be flexible so our athlete can freely move their limb. If we were to use a microchip, the warming device may still feel stiff and uncomfortable, and there is a chance that the microchip would not stay in place. As for the third design, our heating wire element, the issue of using it was the potential of creating hot spots which may cause burns. Similarly, when we discussed our athlete about our designs, he expressed that to not use the heating wire elements because he was concerned about the hot spots as well. So ultimately, we chose to use heating pads with insulating and wicking materials, as there are many heating pads available in the market which are small, thin, lightweight, and inexpensive. It is also flexible, which best suits for our design and for our athlete to move freely, and we are able to control the precise temperature that it can emit.
Now we will move on to computational modeling and results. For the current COMSOL simulation, the team used the convection and conduction to simulate the passage of heat through each layer of the device, including the skin. The top image depicts heat dissipation in the insulation layer, and the bottom image depicts heat dissipation in the bottom of the skin layer. For the next step, the team will need to collect data below the wicking material layer and to perform time-dependent studies to model the rate that the skin will heat and cool. The tables shown depict the temperature recorded in COMSOL versus the distance away from the center of the heating element in centimeters. At 5 centimeters, it was shown that the heat began to decrease, and at 6 centimeters away from the center, the heat reached the threshold of around 35°C.
This is the LT-SPICE simulation of the heating pad showing how the current flows through it. The V2 power source simulates how we will control the heating pad by turning on and off the power source to the MOSFET. It will also take into consideration the 5-second heat up speed. Of course, we will need to do more testing on how fast the heating pad will actually heat up and cool down, but overall, the maximum current going through is 828. Using the datasheet and the max current, we can estimate the max temp will be about 60.26°C. However, we should take into account the R² values less than 0.95.
Developed 3 total prototypes for this project so far. Prototypes 1 and 2 are the looks and feels like prototypes. The first prototype focused on visualizing the concept and emphasizing the shape of the device and its components. Prototype 2, however, is focused on the layers and the location of each of these components. Specifically, it focuses on user comfort and ergonomics. For prototype 3, we developed a cross-section of our final device including 4 layers: synthetic skin, wicking material, the heating pad, and insulating material. On the right you will see a model of our circuit which includes a MOSFET for heating pad control, a button for device control, a thermistor for temperature sensing, and the heating pad itself. The prototype aims to test whether the device is able to power off when the skin temperature exceeds 37 degrees and power on when the skin temperature is lower than 35 degrees Celsius.
This is the circuit that we created. The heating pad is in a pocket-like structure to mimic the 3-layer structure that we'll be using for our next prototype. And then we have the thermistor right below the pocket to measure temperature. This is the GUI that we created. It tells us if the system is on or off. The graph is only for visualization purposes, but to actually know the temperature, we look at the left panel. Currently the system is off, but when I press the button, the system turns on and it starts plotting the temperature on the graph. As soon as the temperature hits 37, the heat turns off, and as soon as it hits 33, the heat turns back on, and there are clear timestamps denoting each and every event. In this experiment, the system started at 0 degrees Celsius for the first 17 seconds, remaining off. At around 17.7 seconds, it rapidly heated to 29.47 as the system turned on. Over the next 80 seconds, it gradually warmed to an operating range of 33 to 37 degrees Celsius. From then, 100 seconds onwards, the temperature stabilized around 35 degree with only plus minus 1 degree variation, showing excellent thermal stability. The experiment lasted about 22 minutes with 2,172 data points sampled at 1.66 Hz.
The success criteria for our product includes providing safe warming to the residual limb, having functional and effective heating, ensuring that this product is easy to use, and making the product so that it is comfortable inside or paired athlete's prosthetic socket. To ensure we achieve these success criteria, we will make it so that our product maintains the residual limb temperature at 34 to 36 degrees Celsius, that it reaches this temperature in 5 to 7 minutes, that it includes a small rechargeable battery that lasts for over 2 hours and is less than 150 grams and is thin enough to fit inside the socket.
We created a Gantt chart to keep track of the things we want to do for each prototype. For this semester, we created 3 prototypes as shown previously. So for the next semester, we plan on creating 3 more prototypes and wrote down what we would like to accomplish for each one. So for prototype 4, we plan to discuss about the bill of materials to order before the semester begins. We also plan to implement safety measures and a Bluetooth app controller, as well as conducting more tests for our materials to get closer to our goals. As for prototype 5, we plan on creating the whole warming device where it has its 3 layers and to conduct testing with our athlete. Lastly, prototype 6, we hope to complete the warming device to be ready for the competition. Thank you for listening.